Hi there, Joshua here. I had my nephew round today and I said, I'm just popping out, can you cook these chips and we'll have them when I get back? I said, I'd like you to set the oven to 180 degrees. When I got back, he hadn't cooked the chips, he'd just turned the oven round. Let's get on with the lesson. So welcome to lesson 2 on advanced trigonometry. What I'm going to do in this lesson is I'm going to first of all quickly recap what we did in lesson 1, which was I showed you sort of how to define sine, cos and tan for all angles as you go round and round a circle. So I'm going to quickly recap lesson 1, and then I'm going to show you a much easier way of picturing sine, cos and tan. So let's do a quick recap of lesson 1. So if you remember in lesson 1, I sort of showed the angles by drawing a quadrant diagram. So it's a diagram with 4 quarters or quadrants. This is the first quadrant, second quadrant, third quadrant and fourth quadrant. And angles are measured always from this horizontal line. Positive angles are measured in the anti-clockwise direction. So this is 90 degrees, 180 degrees, 270 degrees, 360 degrees. You can keep going, 450, 540, 630 and so on. You can also talk about negative angles by going the other way, by going clockwise. So you always go from this line. So this would be minus 90, minus 180, minus 270, minus 360 and so on. But the important thing to remember is angles are measured from this horizontal line. So so last lesson I was showing you how to define sine, cos and tan for all different sorts of angles. So let's start with an acute angle. I'm just going to do like 3 or 4 examples just as a quick recap. Let's start with an acute angle, somewhere between 0 and 90. So let's say somewhere over here. I'll call it theta. And to talk about sine, cos and tan, we need to form a triangle. So we drop a line down to the horizontal to get a triangle. And suppose when I measured the sides, suppose this side was 3 units long, this side was 4 units long, and this side was 5 units long. So how do we talk about sine, cos and tan? We'll just use SOHCAHTOA. SOHCAHTOA. It's just a way of remembering what sine, cos and tan mean. So I need to label the sides, hypotenuse, opposite and adjacent. So this side's the hypotenuse, it's the longest side. This side is opposite this angle, so it's the opposite side, and this side's next to the angle, so it's the adjacent side. So now I can just write down sine, cos and tan. Sine means opposite over hypotenuse, so for this angle, sine theta is opposite over hypotenuse, it's 3 over 5. Cos theta is adjacent over hypotenuse, here it's 4 over 5. And tan theta is opposite over adjacent, it's 3 over 4. So tan theta is 3 over 4, 3/4. Now you can extend this idea, as you saw in last lesson, to lots of other angles, or to all angles as you go round, not just angles less than 90 degrees. So I could draw an obtuse angle and do exactly the same thing. I think I'll do 3 more examples. So if I draw an obtuse angle, so I go to 90 and then keep going a bit more. So let's see, I go to here. I call this angle theta, it's obtuse. It's an obtuse angle. So to form my triangle, you always drop a line to the horizontal. So I'll drop my line down to get my right angled triangle. And suppose when I measured the sides, this side was 5, this side was 12, and this side was 13. I'll label the sides, opposite, adjacent, hypotenuse. Hypotenuse the longest side, so this is the hypotenuse. Now, if you remember from last lesson, even though the angle's outside the triangle, we still talk about opposite and adjacent relative to this angle in the triangle at the centre of the quadrant diagram. So this side would be the opposite side, and this side would be the adjacent side. So the opposite side is always the height of the triangle, and the adjacent side is always the base of the triangle. And also, if you remember from last lesson, if the adjacent side is going to the left, we treat it as a negative number. So here the adjacent is actually minus 5. And if the opposite side's going down, we treat that as a negative number. In this case, the opposite side's going up, so we keep it as a positive number. But had it been going down, we'd actually say it was minus 12. The hypotenuse is always taken to be positive, whether it's sloping that way or whether it's sloping that way. Right, so now we can just write down sine, cos and tan. I think I'll just do sine actually, I'll just do sine theta. Maybe I'll do cos theta there and tan theta there. So sine theta is opposite over hypotenuse, so that's just 12 over 13. 12 over 13. Now, as I said, you could do all sorts of angles, reflex angles. You can even do negative angles. So let's do one of those. You get a negative angle by going around in the clockwise direction. So let's go to minus 90 and a bit beyond. So this angle here is somewhere between, call it theta, somewhere between minus 90 and minus 180, but it's a negative angle. Negative. To form the triangle this time, you have to draw a line up to the horizontal. So you always go to the horizontal. So you draw a line up to get your right angle triangle. And suppose when I measured the sides, this side was 7, this side is 24, and this side was 25. I'm just using numbers, nice numbers that make right angle triangles that work in Pythagoras' theorem. So let's label the sides. So this is the hypotenuse, and this is the opposite side, because it's opposite this angle at the centre of the diagram. So this is the opposite side, and this is the adjacent side. The adjacent side is going to the left, so we treat it as a negative number. So we say the adjacent is minus 7, and the opposite side is going down, so we say the opposite is minus 24. Remember, the hypotenuse is always taken to be a positive number, whether it's sloping that way or that way. So I did sine theta there, let's do cos theta here. Cos theta is adjacent over hypotenuse, so it's minus 7 over 25. Minus 7 over 25. So notice the cos theta is negative, and that's because the adjacent is negative, because it's going to the left. Right, let's do one more example. Let's do an angle bigger than 360. So imagine I go around a full turn with the pen, that's 360, and I go a bit further. So there we go. So imagine doing that. I'll still call it theta. Theta is greater than 360, I'll just make that clear. To form the triangle, you still just drop a line down to the horizontal, and it's exactly the same as before. Suppose when I measured these sides, this side was 6, this side was 8, and this side was 10. I'll just label them. This is the hypotenuse, this is the opposite side, this is the adjacent side. The adjacent side is going to the right, so we treat it as a positive number. The opposite side is going up, so we treat it as a positive number. The hypotenuse is always positive. So we've done sine, we've done cos. Let's just write down tan theta for this angle bigger than 360, tan theta. Well, tan is opposite over adjacent, so that's just 6 over 8. So tan theta is 6 over 8. So what I'm going to do now is I'm going to show you a much easier way of picturing sine, cos or tan by drawing all these angles, all these triangles, inside a circle of radius 1, called the unit circle. So I'm going to do that now. Right, the unit circle. So this time I'm going to draw the angles inside circles. So imagine the quadrant diagram, just like before, but I'm going to draw a circle of radius 1 whose centre is the quadrant diagram. So imagine a quadrant diagram, just like before, but there's a circle around it whose centre is the quadrant diagram, and the radius of the circle is 1. Radius is 1, and we call this a unit circle because the radius is 1 unit. So what I'm going to do is I'm going to draw an angle just like before. I think I'll draw an angle in the 4th quadrant, a reflex angle. So I'll draw an angle down here, a reflex angle. Notice when I drew the line forming the angle, I stopped when I got to the circle. And then I'm going to draw a line to the horizontal to get my triangle. You've got your right angle triangle there. I'll just label the sides. This is the hypotenuse, this is the opposite, this is the adjacent. Now because I stopped when I got to the circle, that means that the hypotenuse is of length 1. It's of length 1 because it's the radius of the circle. So the hypotenuse is of length 1. The adjacent side, suppose I measured that and I found that was 0.8. And suppose I measured the opposite side and I found that was 0.6. They've both got to be less than 1, because the hypotenuse is the longest side, and that's 1. Now the opposite side's going down, so we'd actually treat it as minus 0.6 here. So the opposite is minus 0.6, and the adjacent is 0.8. Let's see what happens if we write down sine, cos and tan for this angle. I'll call it theta, for this angle drawn inside a unit circle. Let's see what happens. Well, sine theta is opposite over hypotenuse, which is minus 0.6 over 1. Well, that's just minus 0.6. Minus 0.6. So sine theta is just this length here. It's just the height of the triangle. So and that's pretty cool. Let's see what I get for cos theta. Cos theta is adjacent over hypotenuse, which is 0.8 divided by 1. So 0.8 over 1. Well, that's just 0.8. So cos theta is just this length here. It's just the adjacent side. It's sort of like the base of the triangle. So it's, when you draw the angle inside a unit circle, sine and cos are just lengths on the triangle. This is sine theta and this is cos theta. What about tan theta? Well, let's do that. Tan theta. Well, tan theta is opposite over adjacent. Opposite over adjacent. So it's minus 0.6 over 0.8. That's the same as minus 6 over 8, which is just minus 3/4, or if you want it as a decimal, minus 0.75. So minus 0.75. So what does that represent geometrically? Well, tan theta is just that divided by that. So that's the gradient of this slope. It's just the gradient, because it's sort of like the change in the, for a line, the change in its vertical position divided by the change in its horizontal position is the gradient. So it seems to be that, well for this triangle here, drawn inside the unit circle, sine theta is the height of the triangle, cos theta is the base of the triangle, and tan theta is the gradient of the triangle. So let's generalise that result using a bit of algebra. I'll just do it over here. Let's generalise that result. Again, I'll draw a unit circle centred at the middle of the quadrant diagram. So again, the radius is 1. It's a unit circle, just means the radius is 1. And I'll sort of draw a general angle now. So I'll call it theta. Again, notice I've stopped when I got to the circle. That just means the hypotenuse will be 1. And I'll drop a line down. So label the sides. We've got the hypotenuse, the opposite, the adjacent side. Now the hypotenuse has to be 1 because it's been drawn inside a unit circle. Because we're talking in general terms, I'll just say the adjacent length is x and the opposite side is of length y. So I'll just use the letters x and y for the lengths of those two sides. Right, so let's see if we can write sine, cos and tan just in terms of x and y. We'll come up with a general result. So I'll just write in a unit circle. In a unit circle, so sine theta, hopefully there's enough room, sine theta equals, it's opposite over hypotenuse, so it's just y over 1. So y over 1, well that's just y, isn't it? That's just y. So it's just the height of the triangle. So sine theta is the height of the triangle, if you draw it inside a unit circle. Cos theta is, well, it's adjacent over hypotenuse, so it's x over 1. X over 1. Well, that's just x, because anything divided by 1 is itself, so that's just x. So cos theta is just this length, it's just the base of the triangle. So let's write that down. Cos theta is the base of the triangle. Base of the triangle. Let's do tan theta. Tan theta is opposite over adjacent. So tan theta is y over x. So it's y over x. And what does that represent? Well, as I said, that's just the gradient of the slope. It's the gradient of the line forming the angle, because it's that divided by that, basically, which is how you sort of work out gradient. So tan theta is the gradient of the slope. So if you draw the angle inside a circle of radius 1 inside a unit circle, you get these nice sort of geometrical representations for sine, cos and tan. Sine theta will be the height of the triangle. It'll be positive if it's going up, negative if it's going down, like it was here. Cos theta will be the base length of the triangle. Again, positive if going to the right, negative if going to the left. And tan theta will be the gradient of the sloping line. And actually, if the line is sloping that way, tan theta will be positive, and if the line is sloping that way, tan theta will be negative. So it always works out that tan theta matches the gradient of the slope. So yeah, that's it. Pretty nice. So what we'll do now is I'm going to draw some actual angles, measured angles inside a unit circle. I'm going to draw them accurately using this. And what we're going to do is we're going to estimate sine, cos and tan just from the picture, just from looking at the picture. And then what we'll do is we'll check the answers against the true values of sine, cos and tan using a calculator. So that's coming up next. Right, my first angle is 30 degrees. I've drawn it accurately using an angle measurer. What we're going to do is we're going to estimate sine, cos and tan of this angle of 30 degrees just using the picture. So what you need to do is you need to imagine it's inside a circle of radius 1, a unit circle. So you've got to imagine the radius length is 1. So from there to there is 1, from there to there is 1, from there to there is 1, from there to there is 1. To estimate sine, cos and tan I need to form the triangle. So I'll drop a line down to form the triangle. So there we go, you've got your right angle triangle. And in a unit circle, sine theta, or sine 30 in this case, is just the height of the triangle. So this height here is sine 30. Remember, the whole radius is 1 unit, the whole radius is 1. So what I'll do is, to estimate the height of the triangle, just to help, I'll draw a dotted line going across so we can compare it with the radius, like that. So if the whole radius is 1, what would you say the height was? What would you estimate it to be? Well, to me it looks about 0.5. And if you press sine 30 on your calculator, you get exactly 0.5. So sine 30 is 0.5. I hope that looks about right. Let's do cos 30. So cos 30, remember in a unit circle, the cos value is just the base of the triangle. So this length here is cos 30. So cos 30 is just the base of the triangle in a unit circle. And remember, the whole radius is 1 unit. So what would you say that length was? Well, it's nearly the whole radius. It looks to me it's about 0.8 or 0.9. I'm cheating because I know what it actually is, but if you do it on the calculator, you get 0.87 to 2 decimal places. 0.87 to 2 dp. Now tan 30 is the hard one to estimate. Tan 30 is the gradient of the slope. So tan 30 is the gradient. It's basically that divided by that, so that's not easy to estimate. I mean, if the angle was 45 degrees, the height and the base would be exactly the same, so the gradient would be exactly 1. So because the angle's less than 45 degrees, we know the gradient is less than 1. But it's difficult to estimate what 0.5 divided by 0.87 is. I mean, it's somewhere between 5 over 8 and 5 over 9. So 5 over 8 is about 0.625 and 5 over 9 is 0.5 recurring. I wouldn't expect you to know those. So the answer is going to be somewhere in between, so maybe around 0.6. Again, I'm kind of cheating because I know what the answer is already. But if you do tan 30 on your calculator, you get 0.58 to 2 decimal places, so 0.58. But as long as you appreciate, it's going to be less than 1. And it's not, it's a bit bigger than 0.5 because the height is more than half of the base. So, yeah. Let's do another angle. This time I measured 115 degrees round from the horizontal. To talk about sine, cos and tan of 115, I need to form the triangle. So let's drop a line down. So we're going to estimate sine, cos and tan for this angle, 115 degrees. And now some of sine, cos and tan will be negative. Some of them will be negative. Yeah, let's use the let's estimate sine 115. So remember, in a unit circle, the sine value of the angle is just the height of the triangle. So this is sine 115. Will it be positive or negative? It'll be positive because the height's going up. So it's going to be positive. And let's estimate it. Remember, you've got to think that the whole radius is 1 unit. So what would you estimate the height of the triangle to be? Well, it's nearly 1, isn't it? It's nearly 1. It looks about 0.9 perhaps, 0.9. And if you do it on the calculator, you get 0.91 to 2 decimal places. So 0.91. So hopefully that looks about right. Let's do cos of 115. So remember, cos is the base in a unit circle. This is cos of 115. Cos 115. There we go. So what would you is it positive or negative? Well, the base is going to the left, so it's going to be negative. So you could think from there to there is minus 1. So what would that be? It looks about minus 0.4, minus 0.5 perhaps. And if you were to do it on the calculator, you get minus 0.42, I think. Minus 0.42. Which just means it goes 0.42 to the left. So that's cos of 115, it's negative. Tan 115 is the gradient. Tan 115, we can estimate that. Is it going to be positive or negative? Well, the line is sloping down. It's sloping down quite steeply, so it's going to be negative, and it's going to be quite steep. Again, it's just that divided by that. Ignoring signs, 0.42 goes into 0.91 about a bit more than twice. So the gradient is going to be about, well, it's going to be a bit more than minus 2. It's quite difficult to estimate it accurately, but yeah, and if you do it on the calculator, you get minus 2.14. Minus 2.14 is the gradient. Let's do an angle in the third quadrant. So my next angle is 230 degrees. It's been measured accurately from this horizontal line round into the third quadrant there. So to estimate sine, cos and tan of 230, again I'll draw the triangle by drawing a line up to the horizontal this time. You always go to the horizontal. Again, we're imagining we're inside a unit circle of radius 1. So let's estimate sine 230. So sine of an angle is just the height of the triangle if it's drawn in a unit circle. So this height here is sine 230. Now, is it going to be positive or negative? Well, this time the height's going down, so it's going to be negative. And to help estimate it, I'll just draw a dotted line across so you can compare it with the radius. Remember, from there to there is sort of the whole radius, so it's minus 1 all the way down. So to estimate sine 30, you've got to think, what's the distance from there to there? Well, it's about minus 0.7, minus 0.8 perhaps. And if you do it on the calculator, you'll get minus 0.77, minus 0.77 to 2 decimal places. Let's do cos 230. So in a unit circle, the cos value of the angle is just the base of the triangle. So it's just this length here. This is cos 230. Again, is it going to be positive or negative? Well, this time the base is going to the left. So the cos value is going to be negative again. And you've got to think, well, from here to here is minus 1. So what's the distance from here to here? What's the base length going to be? Maybe about 0.6, 0.7, something like that. I am cheating again because I know the answer. If you do it on the calculator, you get minus 0.64. Minus 0.64. Right, let's estimate tan of 230. That's just the gradient of the slope. So tan 230 is the gradient. So first of all, is it going to be positive or negative? Well, if you notice, it's sloping upwards. It's sloping in the positive direction. So the tan value is going to be positive. The gradient is basically that divided by that. So ignoring signs, it would kind of be like, well, it's kind of like this divided by that. Ignoring signs, 0.64 goes into 0.77 a bit more than once. So the gradient is going to be a bit bigger than 1, but it's quite difficult to estimate it accurately. It's going to be a tiny bit bigger than 1. And if you do it on the calculator, you'll get 1.19 to 2 decimal places. So the gradient is 1.19, which hopefully kind of makes sense, looks about right from the diagram. Right, let's do an angle in the fourth quadrant. So as you can see, I've drawn a negative angle in the fourth quadrant by going clockwise round. So the angle is minus 45 degrees, so it's just 45 degrees clockwise round. Let's form the triangle and then estimate sine, cos and tan for minus 45 degrees. So here's the right angle triangle. So sine of minus 45 degrees, because it's in a unit circle, is just this height, it's just the height of the triangle. This is sine of minus 45 degrees. Again, to help, I'll just draw a dotted line across, so you can compare it with the radius length. So first of all, is it negative or positive? Well, it's going to be negative because the height's going down. So from there to there is minus 1. So what's the height? What's it going to be from there to there? Maybe about minus 0.7. I'm cheating again because I know the answer. On a calculator, if you do it to 2 decimal places, it's minus 0.71. So it's minus 0.71 to 2 decimal places. Now what about a cos 45? Well, cos 45 is just the base of the triangle. So is that going to be positive or negative? Cos of minus 45. Is that going to be positive or negative? Well, the base is going to the right, so this time the cos value is going to be positive. And we don't even actually need to estimate it now that we've got that answer, because what sort of triangle is this? Well, it's actually an isosceles triangle, because if this angle's 45, that means this angle's got to be 45 as well, because they've got to add up to 90 to make 180 with that 90 there. So because it's an isosceles triangle, ignoring sines, this length is actually exactly the same as that length. It's just cos is going to be positive, so it's going to be 0.71 to 2 decimal places. You can check it on the calculator, but it is 0.71 to 2 decimal places because you've got an isosceles triangle there. What about tan minus 45? That's just the gradient of the slope. Tan of minus 45 degrees. Is it going to be positive or negative? Well, it's sloping down this time, so it's going to be negative. Again, we don't actually need to estimate it. We've got all the information here. Basically, the height and the base, ignoring sines, are exactly the same, which means that the gradient is going to be exactly minus 1. It's sort of like that divided by that is minus 1. And you can check that on the calculator. Tan of minus 45 degrees is minus 1. It's sort of like a perfect diagonal line going down. Let's do one more angle. So for my final angle, I've measured 20 degrees around to this line, but I'm not going to mark 20 degrees. I'm going to do a full turn first. So I'm going to do a full turn, then an extra 20 degrees. So what angle is that? Oh, well, it's 360 plus 20, so it's 380 degrees. So let's estimate sine, cos and tan of 380 degrees. So it works in exactly the same way. Just draw a line down, form the triangle. There we go. This is our triangle. And sine 380 is just the height of the triangle. This is sine 380. Again, to help estimate it, I'll just draw a dotted line across to the radius. So is it going to be positive or negative? Well, the height's going up, so it's positive. So the whole radius is of length 1. So what would you estimate that length to be, the height of the triangle? Well, if you do it on the calculator, you get 0.34. 0.34 on the calculator. Cos 380 is just the base of the triangle. So it's just this length here. This is cos 380. Cos 380. So what would you estimate that to be? Well, it's very close to 1, isn't it? I mean, 1 is the whole radius, and it's nearly the whole radius. It goes right up to there. And if you do it on the calculator, you get 0.94. So it's very close to 1, 0.94. Now tan 380, again, tan is kind of difficult to estimate. It's the gradient of the slope. So tan 380. So if the line was there, if the line was perfectly diagonal at the 45 degrees position, then the gradient would be 1. So we know the gradient is less than 1. And the gradient is basically, it's just that divided by that, which is kind of roughly a third. I mean, 3 divided, so 0.3 divided by 0.9, or 3 divided by 9 is a third. So it's going to be roughly a third, or roughly 0.33, a bit more than that. And if you do it on the calculator, you actually get 0.36. 0.36. So I should just mention, because you might be thinking, couldn't we have used this, this triangle to estimate sine, cos and tan of 20 degrees? And yes, you can, because this angle is 20 degrees. So sine, cos and tan of 20 degrees would be exactly the same as sine, cos and tan of 380 degrees, because it's exactly the same triangle. So this is sine 20, 0.34, this is cos 20, 0.94, and tan 20 is 0.36. So it's exactly the same. So if two angles are 360 degrees apart, their sine, cos and tan values are going to be exactly the same, because you can use exactly the same triangle. So another way of putting that is that sine, cos and tan repeat every 360 degrees. As you're going to see when I draw the trig graphs next. Right, what we're going to do to finish off is we're going to draw, well, I'm going to have a go at drawing the trig graphs. So the graph of y equals sine theta, y equals cos theta, y equals tan theta, just using what we've learnt about the unit circle. So some of you might know what these graphs look like, but you might not have seen where they come from. So I'm going to use the unit circle to explain where these graphs come from. So let's start with sine theta. Remember, the values of sine theta are just the heights of the triangles as you go round the circle, basically. So let's think what happens to the heights of the triangles as you go from 0 to 90 degrees. I'll just draw some triangles and see if you can see what's happening to the heights. Well, the heights start off very small, very close to 0, and as you increase the angle from 0 to 90, the heights increase and get closer and closer to 1. They get closer to the radius of the circle. So the heights basically go from 0 to 1. So as you go from 0 to 90, the heights go from 0 to 1, like that. And then as you go from 90 to 180, let's see what happens to the heights of the triangles, the sine values. So hopefully this isn't too confusing. So as you go from 90 to 180, you can see that the heights of the triangles are getting smaller and they're going back down to 0. So the graph sort of does that. And then as you go from 180 to 270, 180 to 270, let's see what happens to the heights of the triangles. I'll just draw some more. So I'll slowly increase the angle from 180 to 270. You can see that the heights of the triangles increase, but in the negative sense. They sort of get closer and closer to -1. So they go from 0 to -1, so -1. And let's see what happens to the heights of the triangles as you go from 270 to 360. So again, I'll just draw some triangles. And hopefully you can see that the heights are going back to 0, basically. They're going from -1 to 0. And you can keep going round and round in either direction. So the graph does continue like this. It's like a wave, a continuous wave. And this is the graph of y equals sine theta. Now, you might be thinking, how can I talk about sine 0, or sine 90, or sine 180, or sine 270, and so on? Because when the angle is 0, or 90, or 180, or 270, or 360, there is no triangle. There's sort of just a flat line. So at 0, so there's just a line. As you go to 90, there's just a line. As you go to 180, there's just a line. But you can still talk about sine 0, sine 90, sine 180, just by thinking about what happens to the triangles as you get closer and closer to those angles. So for example, I said sine 90 is 1, and that's because as the angle gets closer and closer to 90, the heights of the triangles get closer and closer to 1. So it makes sense to say sine 90 is 1. Similarly, I said sine 180 is 0, and that's because as the angle gets closer and closer to 180, the heights of the triangles get closer and closer to 0. So again, it makes sense to say sine 180 is 0. And I'm going to be doing the same with cos when I talk about the bases of the triangles. So let's draw the cos graph now. So the cos, in this unit circle, the cos values are just the bases of the triangles as you go round and round the circle. So let's see how the bases change as you go from 0 to 90. As you go from 0 to 90. So let's just draw some triangles and see if you can see what's happening to the bases of the triangles, how they're changing. Well, you can see that the bases start off quite big, quite close to 1, and the bases get smaller and smaller and closer to 0 as the angle goes from 0 to 90. So the bases basically go from 1 to 0. From 1 to 0 as you go from 0 to 90. Then as you go from 90 to 180, what happens to the bases of the triangles? Well, let's draw some triangles again. Well, you can see the bases sort of get bigger, but in the negative sense. So they sort of go to -1. So as the angle goes from 90 to 180, the bases go from 0 to -1. So the graph does that. And then as you go from 180 to 270, let's see what happens to the bases of the triangles. I'll just draw 4 triangles in this quadrant. Well, you can see the bases, as the sort of triangle gets taller and thinner, the bases get sort of go from -1 back to 0. The bases get smaller and go back to 0. And as you go from 270 to 360, let's see what happens to the bases of the triangles. I think you can see where this is going. So the bases actually get bigger as you go to 360, and they get closer and closer to 1. And again, you can keep going round and round the circle in either direction, so this graph will continue. It's a wave. It's basically the same as the sine graph. If you were to move that, if you were to shift that 90 to the left, you would get this graph. So they're very similar. Right, so that's the sine graph, that's the cos graph. Let's do the tan graph. Now the tan graph is very different to the other two. Before I draw it, I need to draw some dotted lines, some vertical dotted lines at certain points. So I need to draw it at -90. You'll see why I'm doing this in a minute. At 90 and at 270. So intervals of 180 degrees. I'm drawing these dotted lines. So the tan values of the angles are just the gradients of the slopes. They're sort of the gradients of the lines that form the angle. So I don't really need to draw triangles, I just need to draw the lines that form the angle and see what happens to the gradients as I go round and round. So let's do that. So let's think what happens to the gradients of the slopes as I go from 0 to 90. Well, at 0, it's just a flat line, so the gradient is 0. And then as you increase the angle, the gradient sort of gets steep, that gets bigger. So for example, tan 45 is 1. When the angle gets to about 60, the gradient is 2. And the gradient keeps increasing more and more and more and gets big. There's no sort of upper limit. It gets the gradient gets bigger and bigger and bigger and bigger. And eventually you get a vertical line. The gradient of a vertical line is sort of undefined. So tan 90 has no value. If you press tan 90 on the calculator, you'll get an error message. But as you get closer and closer to 90, the gradient, or the tan value, gets bigger and bigger and bigger. So if you were to do tan 89, you'd get a very big answer. So as the angle gets closer and closer to 90, the tan value, or the gradient, gets bigger and bigger and bigger, and there's no upper limit. The closer you get to 90, the bigger the gradient will be. So that's what happens as you go from 0 to 90. I could draw some lines in actually, so you can see how the gradient is changing as you change the angle. Let's see what happens as you go from 90 to 180. And I'm actually going to think of this backwards, so I'm going to start at 180 and go backwards to 90. At 180, the pen is flat, so the gradient is 0, so the tan value is 0. And then as you go from 180 to 90, what happens to the gradients of the slopes as you go from 180 to 90? Well, you can see that the gradients get steeper and steeper and steeper, but in the negative sense. So the gradients go from 0 to -infinity, because there's no limit again to how steep the line gets. So the gradient goes from 0 to -infinity. The closer you get to 90 from above, the more negative the gradient will be, and there's no lower limit. Right, let's think what happens now as you go from 180 to 270. So as I said, at 180 the gradient, or the tan value, is 0, because it's just a flat line. And then as you increase the angle, as you go to 270, what happens to the steepness of the line? Well, as you can see, the line gets steeper and steeper and steeper, and the tan values, or the gradients, get closer and closer. Well, they go to infinity, from 0 to infinity. So the tan values get bigger and bigger and bigger, and there's no upper limit. And then as you go from 270 to 360, again I'm going to do this backwards. I'll start at 360. So at 360 the gradient is 0, and then as you go to to 270, you can see the gradient gets more and more negative, steeper and steeper and steeper, but in the negative sense. So we say the gradient goes to minus infinity. So at 360 the gradient is 0, and it goes to minus infinity. It gets more and more negative as you get closer to 270. So again, you can keep going round and round the circle, so the graph does continue like this. So it's a series of separate curves like this. So that's the graph of tan theta. So there are the trig graphs. So now you know where they come from. That's it.